For me, uh, for B, right? B is if my origin is beach, then okay. That. So think this one is 110. On the left side is gonna be okay. X equal to -1, isn't it? Okay, and then y is equal to, what is it? Y is equal to this one, 3, 4, 3. Okay. So yeah, it's correct. Because what is it? This one. I think you are correct, L. Okay. Because you make a new cubic, isn't it? L. You make
Yes, yes, yes.
the position of a y is not similar, isn't it?
Yes.
Is
One
that
is
your idea?
1.3.
Yeah,
Yeah. First one
that
is
is correct.
1.3
Okay.
and another is
Yeah,
3,
yeah.
4.
Okay. Thank you. Thank you. You make me realize. Okay. Sorry. A new origin, but I think you can make. I think that is correct. Okay. Okay. That is correct. So you just want to make. That is okay. So you just make it. You want to make it a similar. Okay. So that means this one y is equal to 512. Okay, 1 and infinity, z infinity, x equal to 1. Okay. This one is the origin is from here, isn't it? This one is the new origin. Okay. So better you write the origin. What is your origin? The position? You
I
don't
don't
remember.
know.
Okay. So
Uh,
but here, what is the new for the new origin? So I think it's correct. This one. Okay, because the position is not set. Okay. 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 For C is gonna be the C is yeah infinity as well as D. think Can you see my Padlet? Okay, for the answer. Thank you. Okay. Let's see, we continue on the volume, planar, and linear density of unit cell. Once you determine the direction as well as indices, you can calculate this volume, planar, as well as indices. So the example of volume density, okay, volume density is, yeah, you know what is the volume, right? Okay, volume is the mass per volumes, density, okay? Density is the mass per volumes, okay, the unit, okay, rho equal to m divided by A. So for example, for this one, Cooper, okay, Cooper have a unit cell of FCC, first cubic center, okay, has atomic mass, okay, 63.54, which is, or we call it molecular number, gram per mole, okay, or atomic number, and atomic radius 0.1278 nanometer. Find volume density of Cooper. So what you have to do, you have to determine the mass of the unit cells as well as the volume of the unit cells. So as okay, the lattice constants for the FCC is equal to, so just refer to FCC again, A equal to 4R divided by square root 2. So just substitute this radius into the lattice constant equation. So we can get the lattice constant. Okay, and calculate the volume of the FCC. Okay, if you remember FCC, they have the volumes, if you remember, okay, based on the lattice constants, okay, A power of 3. Okay, so you just substitute. So we can get 4.7 4.7 times 10 negative 29 cubic meter. Okay, so please remember that FCC have 4 atoms per unit cell. Refer against for the previous for the FCC per unit cell. Okay, the mass, since we have 4 atoms per unit cells, okay, 4 atoms per unit cells times with the atomic number or molecular number, okay, and divide by 6.23 times 1023 Avogadro number. Okay, so we can get the mass per unit cell in gram. So you can substitute into this equation as well as the volume into this equation. Okay, the answer. Okay, so this is the answer V. Generally, we use a V here, rho V, or we call it a volume density equal to 8.98 gram per cubic centimeter. The voice is lagging. Is it okay? My voice? Is it still lagging?
Oh, okay, Doctor.
It's okay.
Okay, okay. Just some technical problem. Okay. Okay. And then that one is a volume density. How about the planar density? Okay, planar density is based on the Miller indices. Okay, or the plane, based on the plane, planar. Planar is equal to plane. Okay. So if you know the how to determine the Miller indices or plane from the Miller indices, okay, we can calculate the atomic density. So for example, this one, okay, calculate rho PD. PD is a planar density, rho PD, okay, on 110 plane of the BCC. So you have to refer to the body center cubic for the equation, okay, and the lattice constants as well as the volume. Okay, okay, iron, okay, ferrum lattice constant A equal to 0.2887 nanometer. Okay, so what is the equations is rho PD is equivalent number of atom whose centered are by the given planes divided by area of the given center are intersect by a given planes. Okay, this is the center of intersect by given plane. Okay, you have to remember, once you determine the plane by using a Miller indices, this is the atom that intersects. Okay, so they have 1, 2, 3, 4. Okay, 4 for 1 for atoms and 1 is for full atoms. Okay, so you have to see this one. So total is 5 atoms. Okay, because 4 for atoms and 1 for full full atoms. Okay? And equivalent number of atoms in plane 110. Since we have since we have a 4 for 1 for atoms, so if you combine this one, is become one full atom. Okay, one full atom. Okay, so total is going to be this one with another atoms is going to be 2 atoms. Okay, and the area, if you look at here, okay, this one times with this one. Okay, you have to remember that one, since this length is equal to square root 2a and times with this one, because this one is plane, right? So this is the height, this one the length. Okay, so just times you can get the area. Okay, since we need the area. Okay, so just substitute to the equations. If you look at here, equivalent number of atom intersect, so equal to 2. Okay, so just substitute to this. Okay, as well as this one. Okay, the area. Okay, so you can calculate. Okay, so we can get 7. Okay, meter. So this is for standard atomic density. So just remember this equation, rho PD as well as rho V for volume density. Okay, so how about the linear density? Linear density based on the Cartesian coordinates or direction indices. So if you look at here, for linear indices, okay, calculate the linear density of the FCC Cooper crystal along with the 110. Okay, if you look at here is a square bracket represent as a direction indices. Lattice constants A equal to 0.361 nanometer. Okay, rho L equal to number of atomic diameters intersects by selected length of line in direction of interest. Okay, for the planar is a most number of atoms whose center are intersects, right? Is based on the given plane. Okay. Okay. And one full diameter. Okay. So if you look at here, half and half. Okay. So we can get 2 atoms. Okay. Two full, not 2 full atoms, 2 full diameters. Okay. So if you look at here, if we combine this one, half this one. Okay. As well as this one. Okay. Okay. So this is 1, 2, this one is 3. Okay. So if you look at here, this one is 1 full half diameter. Okay. This one full diameter. Okay, so we have 2 full diameters for 2 atoms. Okay, and the length is square root 2a. Okay, this one the length. So just substitute, we can get 2 atoms with 2 full diameters. Okay, divide by square root 2a. So we can get 3.92 atoms per nanometer. So this is the 3 equations for the density. Okay, which is a volume density, planar density, as well as linear density. So please remember, linear density is based on the direction indices. Okay, as well as planar density is based on the Miller indices. Okay. Okay, so let's see the density of the material classes. Okay, look at here. Definitely, if you see metals, the density is much greater than the ceramics. Okay, while ceramic is much greater than polymer. Even if you just see around you, can see metals and as well as what is it? Some ceramics. Okay, so you can compare in terms of which one is more which one is more lighter or much heavier? Is it metal or ceramic? You can compare. The density metals alloys between around 2, okay, around 2 to 20 something, more than 20, okay, a gram per cubic centimeter, due to the cross packing of metallic bonds or large atomic mass, okay. And for the graphite for the for ceramics, okay, due to the covalent bonds, okay, often like the elements, okay. And then so polymer, okay, if you look at here, is much less dense as compared to ceramic as well as metal. This is due to the poor packings. Often is amorphous, okay. Like the elements is organic CHO. Look at here, okay, mostly is organic, okay. But silicon, PVC, PC, okay. And so composite is an intermediate value. We get here composite like carbon fiber, okay, aramide fiber, as wood, okay, GFRE reinforced, okay. So the density of the metal classes, okay. So you can get here, but generally, if you even you can observe by yourself, you will know that metal is much there. Okay, so let's do this tutorial 8. Okay, we do the together and paste in the Padlet. Okay. For the density FTC platinum in grams is a constant A, okay, 0.392399 nanometer, and its atomic mass of 199.09 gram per mole. Okay, can you calculate? Okay, calculate the value of the density. This is by using the volume density. Okay, gram per cubic centimeter. Okay, so if gram per cubic centimeter, the unit is volume density. Okay, this one. Okay, if you look at here, so that means this problem is for volume. Just okay, how to calculate the how to determine this density. I think it's just follow the previous example. Okay, and then you on the Padlet. the sum of in the oh, okay, so when it's like L to similar just by using this one. You can get the okay. And already prepared that. Tutorial 8 is quite easy. Okay. So I the hint. So what you have to do is if you remember is rho v, okay, is equal to mass per unit cell divided by, right? Okay. So how to determine the mass per unit cell? Okay. So since we have four atoms per unit cell, okay, times with, is it? We have to times with the atomic mass. Okay. So this is the atomic mass. Okay, times with the atomic mass. Okay. So you can get the mass per unit cell. Okay. Yes, mass per unit cell. Okay, mass per unit cell. This one. Okay. And then density is this one, lattice constants, O of 3. Okay, so just substitute rho v. Okay. Oh, sorry. This one it should be divided by Avogadro number. Avogadro number. Okay. So and then just substitute this one. Rho v divided by A. Okay. So you can get the answer. Okay. Anyone? Okay. Rho v 21.45. Yes. 21.45. Okay. I hope you can get this answer. Okay, thank you. Okay, how about 9 and I think 9 is similarly, okay, is calculate the value of the relative atomic mass. Still, is give the questions give the density, volume density 16.6 grams per cubic meter. So this one is the back calculation, I think. Okay, is given the rho v. Okay, so what you have to do is for BCC cells. Okay, so for BCC cells, okay, if you remember rho, the equation for volume density, rho v is equal to, okay, mass per unit cell. Mass per unit cell. I just make it what is it? Make it symbol. Okay, mass per unit cell. Divide the volume per unit cell. Volume per unit cell. Okay. So just rearrange these equations. Okay. Mass per unit cell equal to rho v times width volumes per unit cell. Okay. So you have to substitute this density. Okay. And what else is given? Volumes. Volumes, this one. Okay, A O of 3. Okay. And then yeah, this one is, please remember this one, the unit should be similar. Okay. So you can get mass per unit cell. Mass per unit cell. Okay. In gram per unit cell. Okay. Since there are two atoms for BCC, okay, if you look at here, there's a two atoms. Okay. So the atomic mass is gonna be atomic mass equal to, okay, just take this value. Okay. It's just a backward calculation. Okay. This one. Times with Avogadro number. Okay. And divide by two atoms. Two atoms. So you can get atomic mass. Okay. So please do. Okay. So the unit should be gram per mole. Atomic mass is what is it? The atomic weight. Almost similar. Atomic weight or molecular weight. Molecular weight is for molecule. Okay, but for atom is atomic mass. Atomic weight. Okay. So you can get the atomic mass. Okay. The difference 8 and total nines, this one is given, right? The atomic mass. Okay, but this one, the density is given. So just back calculation. Okay. So what's the answer? Okay, give me the answer. Can you give me the answer? The Padlet. One hundred 09. Okay, good. Okay, that is the answer. Please refer to the Padlet. Okay, Vera. So thank you for the answer. Okay. Okay. So just follow the step that I already explained to you. Use gram per mole. Okay. Okay, thank you, Vera. Okay, how about tutorial 10? Okay. So calculate the planar atomic density in atomic per square millimeter for the following crystal planes in BCC chromium. Okay, please remember BCC, body centered cubic, which has a lattice constant of 0.28846 nanometer. Okay. Abdul Rashid also. Thank you, Abdul Rashid. So the answer is 180.09 grams. Okay. So for A is 100, B 110, as well as C 111. Okay. How do you calculate this one? Okay. It's gonna be a different angle or different planar, different planes. Okay. You have to uh, draw first or sketch the cubic or the cube of the uh, what is it, by using the Miller indices. Okay, for example, this one A, what is the Miller indices or the plane of the cubics? Okay, so can you draw and then uh, determines the planar density? Okay, so if you back here, I just give you what is it, some one example. Okay, if 110, okay, if 110, get here, I think this is easy for 110. 110 is easy. The problem is to sketch this one. Ish. Okay, okay, this is your origin. Okay, so, sorry, this is your origin. If 110, that means, okay, x-axis is 100%. Okay, this is 100%, while 0 0, so is 0 for x-axis and y for y-axis. So that means your plane is gonna be here. This is your plane. Okay, this is your plane. Okay, so you have to identify how many atoms is on how many atoms here. Okay, if you look at here, okay, on planes on the they have only 1 4 1 4 1 4 and 1 1 4. Okay, one is we have at the corner we have 4 atoms at corner, 4 atoms times with 1 4. Okay, atom per corner. Okay, so this is equivalent with one atom. Okay, so please remember, okay, because it's just cross at the corner of the cubic. Okay, so they have 4 atoms, 1 for atoms at the corner. Okay, 4 for 1 for atoms at the corner, so equivalent with 1 atoms for BCC. So once you determine the number of the atoms, okay, you can calculate the based on this expression. Okay, we determines one full atoms is equal to equivalent number of atoms is equal to 1. Okay, if you look at here, this one is equal to 1 for BCC. Okay, for the plane 110. Okay, and the area, how about the area? Okay, the area is just A times width. Okay, so A square. Okay, so A square. So this one. Okay, this is A square. Okay, this one is equal to 1. Okay, so you can get planar density for 110. Can you calculate? Can you calculate? A is 3.4. Who's that, Lukman? No. Okay, Lukman, I don't think so. Your lattice constant is 0.28 through 884. Is it?
Sorry, doctor, I used the wrong formula.
Wrong equation. Wrong formula. Okay. So rho PD equal to the equivalent number of atom. Okay. I just make it short form. Equivalent number of atom divided by area. Selected area. Okay. So area is just okay. The power of 2. Equivalent number is equal to 1 atom. Okay, so just substitute this one. Okay, what is the answer? And the unit should be atoms per millimeter square or any unit, this one, or you want to use a centimeter or meter, is up to you, but I think it's a millimeter square. Okay, nanometer, this one is I'm not sure, I think this one also nanometer. Okay, please check the unit. Okay, anyone post already the answer? 12.02 what is it? Nanometer square. Okay, yes, thank you. Who's this one? Okay, so 12 meter square. Okay, so you so the answer is already post in the Padlet. Okay, so for me I just write 1.202 times is 13. Okay, atoms per millimeter square. Or similarly 12.02 atoms per nanometer square. Okay. Okay. So how about B? How about B? Can you imagine the planner? Yeah, thank you, Hanum. Check also, yes, correct. Okay. Yeah, that is correct. Okay, the answer. How about B? How do you draw the planner? How do you draw the plane? Okay, can you tell me? 110. Like this one. Okay, it's the same. Okay, only you change the lattice constants. Okay, it's the same. It's same. This one because it's 110, right? Okay, it's the same. Okay, you just refer this one and change the lattice constant, so you can get the answer. There's no need for B. So how about for C? C is quite tricky. How about C? What is the plane? How's the plane? Can you sketch the planes and determines the planar density? Can you sketch and then calculate and then post in the Padlet? I want to see the sketch. 111. And how many atoms this one? 110. I don't want 110. 110 you just the what is it, the lattice constant. Okay, it's easy. How about C? Can you sketch and post in the Padlet? One. Anyone can post in the Padlet? How do you draw? How do you sketch the plane with the Miller indices 1, 1, 1? Okay. Mhm. So is 100% x-axis, 100% y-axis, 100% z-axis. Okay, so if you look at here, 100%, if this one is the origin, 1, 0, 0, 0. Okay, so 100% here, x-axis, 100% for y-axis, 100% for z-axis. So what is the plane? One already post independent. Okay, that is correct. Anonymous, but you have to answer. Let me stop this sharing. Okay. P5, the answer. Where is it? 3.5 atom. Why 3.5 atom? Yes, this one is correct. Yeah, but I don't think so it's gonna cross the middle. This one is BCC, isn't it? Yeah. BCC or FCC? Okay, it seems like cross or not? I think it's not cross. Okay. Okay, so it should be like this same. Okay, like this one. Okay. And then same. Okay. And the atom, LS atom. This one. Okay. So if you look at here, the equivalent number of the atom is equal to half atoms. Okay, half atoms. Almost half atoms. Okay. 1313. Okay. Well, as maybe a little bit here. Okay. At the center. That's why it's half. Okay. So 1/3, 1/3, 1/3. Okay. And then for the area, okay, so please calculate this area. So you can get the area is equal to, okay, this one half h, right? Okay. What else? You have to calculate this one also. Okay. So you can get the area is equal to area. Root 6 divided by 4a. Okay. So based on the planar density equations, okay, half atoms divided by root 6 or a. Okay. Square. Okay. So this is the equation. Okay. So you can get the answer. Okay. So please proceed. Okay, that is for planar density. Okay. So let's see for the linear density. Okay. Question 11. Tutorial 11. Okay. So tutorial 11. Okay. Okay. So for tutorial 11, please do 100. Calculate the linear atomic density in atom per millimeter for the following direction BCC vanadium, which has a lattice constant of 0.3039 nanometer. Okay. So please remember linear atomic density is based on the direction indices. Okay, and you have to draw also the cubic, okay, or the unit cell, okay, before you calculate the linear density. Okay, just similar like this one. Okay, so look at here, this one is a 110. Okay, but for the 100, what is the linear atomic density? So this one. Okay, so 100, that means, okay, 0 for y, 0 for z, and 100% for y. So we shade this one, this side. Okay, and if you look at here, not shade, this one is just a line. Okay, because this one is linear density. Okay, so if we define this one as a origin, so toward this direction. Okay, so we have only one atom, two atom. Okay, so it's half. This one is half. Okay, not half, one full diameter, sorry. Okay, one full diameter. Okay, so equal to one full diameter, because this one is direction indices or linear density. Okay, so look at here, this one, right? Okay, this one, 1r, 1r equal to one full diameter. Okay, sorry. Okay, so just based on the equations, okay, one full diameter. Okay, so one full diameter divided by A. Okay, the length is equal to A. So that means, okay, so since rho linear, okay, equal to, okay, number of atom is equal to one atom divided by A. Okay, 0.30339. Okay, 0.3039 nanometer. So you can get the answer. Okay. Okay. So it's easy, right? That's what this answer. Okay. Any questions about the atomic density, volume density, planar density, as well as linear atomic density? Is there any questions? Okay. Okay. Similarly, also for B. Okay. Similarly, B or for B. Okay. If you look at here, 100% for X, 100% for Y. Okay. 0% for Z. Okay. What you have to do, you have to sketch first the cube or the unit cell. Okay. If you sketch. Okay. Right. Okay. So if this one is the origin 0, 0, 0. Okay, 100% X here. 100% for Y, but 0% for Z. So it should be towards this direction. Similarly. Okay, how many atoms? This one as well as this one. Because it is just BCC. Okay. So this one is also 1 atoms because of 1 full diameter. This one is 1 R. Okay. This one also 1 R. Okay, 1 full diameter. Okay. Okay, any questions about the planar density? Okay, so just substitute into the equation. If for 1, 1, 1, okay, for 1, 1, 1, okay, you have to sketch like this one. Okay, so please do, okay, this one. Since it's 100% for X, Y, as well as Z. So this one 100%, it should be to this direction. So it's cross the center, okay. So this one also the atom as well as this atom. Okay. Okay. It's gonna be three atoms. So how about the full diameter? Okay. So for the full diameter, this one is half. Okay. This one is half. This one is 1 full diameter. Okay. So it's gonna be 2 atoms. Okay, or 2 full diameter. Okay. Because it's cross the center of the atom. BCC for BCC. Okay. Okay, any questions about the linear density, planar density, as well as volume density? Any questions?
Doktor,
Yeah.
yang linear yang B tu, dia
Uh,
sama dengan example kan? So, dia ada 2 full diameter ke 1 je?
110. This one. Okay, kalau awak tengok kat sini, okay. This one is for FCC. Kan? Do you know FCC? What is the position of the atom? Where is the position of the atom? On the face is gonna be there is each for FCC. There's atom here, atom here, atom here, atom here, atom here, atom here. But for BCC, okay, for BCC,
Dia kat tengah.
dia kat tengah je kan. It's just at the center. There's no on the plane of the cubic, right? Betul tak?
Betul.
That's why is only one atom for one full diameter for the atoms. Okay.
Okay, faham.
Okay, faham eh? Okay. So we just move to the polymorphism. Only 3 slides. Okay, almost finished. Okay, I hope you can understand this volume density, planar density, as well as the what is it, linear densities. I think it's quite easy. Okay. Okay. So let's we move to this allotropy as well as polymorphism. Okay, so polymorphism is actually ability to exist in more than one crystalline form. It actually is depending on the pressure as well as the temperature. Okay, look at here that according to Gibbs-Press rules, the change in crystalline phase are dependent on the intensive variables such as pressure as well as temperature. So I told you. Okay, for example, is the iron. Okay, can exist in BCC or FCC form depending on the temperature. Here are the examples such as titanium, carbon, or other metals. Okay, look at here. This one is at negative 27 degrees C. If you heat it to 112 degrees C, okay, and then 1394 1394 is going to change uh, the crystalline phase, okay, from alpha ion BCC to FCC as well as delta ion BCC. Okay, so it's changed until it's melting, become a liquid for the temperature more than 1500. So that is the definition of a polymorphism, okay, or allotropy for the ion. Okay. So pure solid carbons occur in the crystalline form. Example is diamond, okay, graphite as well as hollow fullerenes. Okay, for example, this one. They have aromatic layers. Okay, weak van der Waals forms. Okay, weak van der Waals bondings. Okay, plain slide easily make good lubricants. What else? Graphite. Graphite is like balls. Okay, like a soccer balls with the carbon 60 to 70. Okay, this one is the fullerenes or buckyball. Okay, so it can be in the many crystalline form. Okay, or crystalline phase. Okay, carbon nanotube tetrahydroca carbon. Okay, and this one is the comparison on the atomic ready. Okay, atomic ready as the crystal structure. Okay, so if you look at here, that aluminium generally is the FCC. Okay, BCC. Okay, FCC, HCF, BCC for the chromium. Okay, platinum, FCC. So you can see the comparison of the metals. Okay. So actually the Miller indices as well as atomic Miller indices as well as direction indices is important for the what is it, to locate the atoms in the cubic unit cells. So how to determine this one? We can use the instruments such as like XRD, X-ray diffractor. Okay, so you can know the position. Okay, either is crystalline structure or amorphous. Okay, by using XRD. Okay, so just like last time I did my not only last time, even now I still use the XRD. Okay, to know the crystalline, to study the crystalline of the cellulose. Okay, because cellulose is quite special. Okay, they have a amorphous and as well as a crystal structure. Okay, so we can know this crystalline structure, or we can analyze by using XRD. Okay, so it's important for my installation. So any questions? Actually, we finish this. So
Sorry dokter,
yes.
yang tutorial 10 tuh yang B, yang 110 itu macam mana?
110. Okay.
Iya.
So for 110, okay, if you sketch the cubic, okay, we consider this one. Okay, 110. I hope you can understand this cube. Okay, so if this one is x-axis, this one is y-axis, this one is z-axis, so 100% for x-axis, 100% for y-axis, but 0% for it. Is it tutorial 10 or 11? Sorry.
Tutorial 10 dokter. Sorry dokter.
Tutorial 10. Oh, okay. Oh, sorry. Tutorial 10. Okay. Total 10 is similar, just similar like this one. Okay, this one, similar. Okay, if total 10, for example, this one, right? It said 110, right? Total 10. Okay, you draw same. Same, you draw same because it's a, is it BCC? BCC, isn't it? Total 10 is a BCC, and the difference is only the lattice constant. Okay? The difference is only the lattice constant, this one, the value of the lattice constant. Okay, so what you have to do, same, you draw similarly, like this one. Okay, you draw similarly, and cross with the one full atoms. Okay, this one full atoms, and 1 4 4 atoms. Okay, so its total is 2 atoms. Okay, so just substitute to this one, and since the area is also similar because it's a BCC. Okay, this one times with this one. Okay, so this one square root 2, and then the lattice constant. Okay, the lattice constant is given 0.28, right? 0.28846. Okay, nanometer. Where? Okay, so just square root. So you can get the answer. So the answer is 1.699 atoms per millimeter square. Or you can convert into nanometer. Okay, similar. Just change this one, this value. Okay, you understand?
Thank you, Doctor. I understand.
Okay. Okay, any more questions? Okay, so what I would like to summarize for this section actually is the main thing is about the type of the unit cells. Okay, BCC, FCC. Okay, HCP. I think we not cover this one for this subject for this part. Okay, if you remember. How to determines the coordination number, okay, as well as APF, atomic packing factor. Okay, so this is to show how many percent of uh, the unit cells was filled with the matter, while the rest is a voids or empty space. So the difference between the unit cells, okay, if you remember, they have FCC, BCC, simple cubics, and based on the Bravais, we have a 14 unit cells type of the unit cells, okay, and the mean is 7, okay. Orthorhombic, what else? What? Uh, Orthorhombic. Remember this one. Okay, rhombohedrals. Please remember this one. Yes, cubic unit tetragonals. Okay, all these difference actually is we can distinguish depending on the angle as well as the length. Okay. What else? Direction indices. Okay, Miller indices. Okay, as well as a volume planar density as well as linear density and polymorphism. Okay, so I hope all of you can understand this section. Okay, and the main part of this section. Okay. Okay, any questions before we stop? Okay, I have another class after this. I think it's quite. Next week we will discuss chapter 4 on the defects of the crystalline structure. Okay, I think it's a very short chapter, I think. Okay, so we can finish within one week. Okay. Any question? So if you have no questions, we end our class today. Okay, for those who still not scan the attendance, I will share again the QR code. Thank you very much, okay, guys. No more question, right? Okay. So if you know questions, thank you very much. Yeah?
No question.
Okay. Thank you. We start our class today. We end our class today. Thank
Thank you,
you very much.
Lecturer.
Okay.